Hello, here are a few slides to explain the PROSEL tool for selecting materials and processes for lightweight composite structures to complement introductory video. So here's an outline of how you could use it. Some thoughts about selecting materials for lightweight composites. Perhaps an oversimplification. But you could argue that the metals world is pretty easy. Very established design tools, very well understood processes. We've got 100 years of steel car bodies, 60 years of aluminium structures. Composites are very confusing. We have had actually 50 years of experience with unidirectional and woven prepregs, but there are new forms of materials, new process techniques, very actively being developed, and the headache is how do you work out which of these may be helpful to you. We've got a very mature composites industry in the UK, but many different sectors with vastly differing materials and processes, and the main differentiator is the value of weight saving. So how to pick a material appropriate to the level of tailoring you'd like to achieve. You could argue very simply that at one extreme we have the Formula One world, sort of racing yachts, Olympic sports, Formula One. Engineers are pretty comfortable of spending in the order of £1,500 per kilogram of finished structure. Airbus themselves, think of super well optimized, fantastic structures. They're pretty uncomfortable with £500 a kilogram. Trying to do much better than that. Car builders like Bentley, very uncomfortable with £150 a kilogram. And then as we get into higher volumes, we find that we need to engineer structures at a far lower cost. The reason for saying this is the materials and processes used by each of the edges of the community are very different, and often materials can be introduced from other sectors at great benefit. The tool, I guess, had three envisaged users. At one end, a very quick sort of director's strategy study, how to move into higher volumes, how to move into new sectors, look at the available kind of options at hand. Young engineers who are tasked with looking at new structures, a few days of lecturing from Bristol, Imperial, Cranfield, but how to impart them with a body of knowledge to help making informed decisions. Perhaps most usefully for those engineers experienced with composites, how to move into new markets using new materials, introducing materials that are relatively unfamiliar. They would all benefit from an interactive tool to rapidly examine relating applications to the whole field of materials and processes. The tool suggests both materials aimed at weight saving and materials and processes aimed at reducing manufacturing cost. So that's in a nutshell what the tool does. So how we built the tool. It's a systematic approach. Tools informed by the creators, sort of 40 years working in the industry, and the challenges and benefits from new materials, design constraints, production issues, complemented by 3 years of pretty detailed conversations with specialists from part builders, part designers, material suppliers, to essentially build up a body of knowledge to be available to new applications. We're looking at various aspects. We're looking at process capability, shape, surface finish, sort of part details, manufacturing characteristics, layout rates, ability to tailor layouts for weight saving, whether we're looking to build things fast or slow at a rate. It's incorporating performance, stiffness, strength, impact resistant are all built into the tool. The issue of tooling, requirements and cost, where different tools fit for different applications, different volumes are embedded. Materials cost and labour requirement. These are areas which are very difficult to establish, very little published in the scientific world. This is really through conversations with suppliers and manufacturers to build in a body of sort of tacit knowledge. 36 factors in total are embedded, but all correlated and arranged in quite a logical way. How does it work? Well, we've got a set of around 200 materials and process options, from the well-established prepreg hand layup autoclave through to stamping of thermoplastics, pultrusion, all the new techniques. These are essentially posted on a wall. Imagine a wall of post-it notes. And as the tool asks you questions about your part or application, we're actually peeling them off, binning them as they fail to meet what you're trying to build. All being well, we're left with some options which are likely to be able to build your part. And from those options, the tool runs two routines, one looking at structural stiffness. So for an equivalent stiffness part, what would the comparative weight of the structure be using all these options? And then a costing routine looking at materials cost, waste, tool cost amortized per part, and labour, both supervision of automated cells through to laborious hand lab that's needed to build your particular structure, but all contained in a tool which is very, very quick to use. I did this cheeky slide for a conference, and that's to say, in today's world, we have a massive headache trying to work out how to pick better materials. Lots of discussions, lots of delays and confusion. But if PROSEL works well for you, it's bringing in a huge field of capability data, rationalizing that into a nice, simple and clear way forward. Here's what the tool looks like. This is the home page. So we have a brief introduction, the team building it, and all being run through a simple dashboard. You'll need to set up a login, very simple, and I'll basically see who's adding into that sort of login list, and then I give a quick click to authorize access, and away you go. Here's a screenshot of my kind of home page. These are a long list of application studies, and to set up a new one, simply click new selection and then follow the tool through. The tool has three main sort of databases. This one here is a snapshot of the processes, so ranging from prepreg autoclave hand layup through to, in this case, press moulding of moulding compounds, and each of these has a series of attributes, limitations and benefits. Alongside that, there's around about 203 materials and process permutations with the capabilities for each. And alongside that, coming up next, critical factor for us is choice of mold tooling. Really confusing area. Good differentiator between a successful and a difficult project. And we have around about, I think, 12, actually 15 types of tool, ranging from single-sided machine steel, tooling block, prototyping, wet layup, glass fiber tooling. The highest cost of which would be probably Yeah, compression RTM or high pressure RTM, precision aligned, massive press based tool tooling. These have basically a set of attributes: shape, surface finish, and cost, investment cost. So quite a useful database embedded there. The process of working out the materials and processes that could be useful goes through 5 stages. First being shape and quality. So in terms of what you're looking for in terms of geometry, size of part, surface finish accuracy, and that's where to start. Put in all the dimensions, and that's basically the first set. The second stage is what kind of weight saving and reinforcement tailoring you're looking to do. So imagine an Airbus wingskin engineer trying to tailor the most highly optimized, smartest, lightest structure they can achieve through to, say, a car roof, how to bash it out fast. So what sort of weight saving you're chasing. Production rate is obvious, absolutely phenomenal differentiator for us in terms of process techniques. So how many you need per year, how many altogether. Assembly options. Generally, the more parts you build, the faster you want to assemble them. And we have options about whether we co-cure parts together, whether we embed inserts. We want matched surfaces, such as by RTM, and ask you what you're looking for there. Quite a confusing area is structural stiffening, where we have a sort of simple shell structures, whether we choose stiffeners, sort of swaging for part stiffening, foams and honeycombs. We can ask you what you're trying to do there and select materials and processes appropriate to those. And then it uses the embedded information to give you a weight and manufacturing cost comparison for the processes it recommends. So here's the first stage of the requirements definition. And we have a series of questions on the left, which are basically going through in turn. On the right, we have this list of, at this moment, 203 process options. And as you go through the questions, it's then reading across to see which of the 203 could or could not build your part. So we have questions of size, thickness, surface finish, radii you're looking to achieve, thickness variability and warpage, tricky area for us. And at each stage you click submit, and then again it just throws away several or many of these options. Second stage of selection involves weight saving. So it asks you about the loading on your part, strength issues, layout angle complexity issues, how you want to tailor thickness. Any of these questions that are relevant to you or you don't want to deal with at the moment, you just leave them blank. The tool doesn't care, but it helps you refine things to a level. We have a simple and an advanced version. This is a shot from the advanced screen. That will become clear as you're using it. You see here that this is the bottom of the selected list, and then gradually through this process, as we answer the questions and press select, the rejected materials list grows longer and longer. This is stage 3, about production rate. How many per year? How many altogether? Assembly options, embedding inserts, co-curing, again differentiating the useful from the unhelpful processes. Each of the materials and process options has an info button, and that info button will say what the features, i.e. benefits, and also the disadvantage of these options. It'll also say when you're in the rejected list why the tool has rejected them, so you can go back and interrogate what's gone wrong, and essentially give you more understanding of how the process is working. Final two stages are our structural approach. It's asking you if you want to use beading, blades, hats, foam, honeycomb. You can leave this blank if you like, but if you do want to focus in on a particular stiffening approach, it'll discard all the options that can't handle that. Last stage is cost comparison, where we're looking at tooling and materials procurement. So we have a high and a low tool quality. So obviously, you can a choice there, and many will choose obviously for the best option. In aerospace, that will be the INVAR kind of low thermal expansion metals, but you can look at prototype tooling, how to build tooling as cheaply as possible. Slightly confusingly, we have in terms of materials cost, it's got three sectors. It's asking you, are you buying your material to go into aircraft, in which case you have a much higher cost because of the traceability. And then we have industrial applications, using highly tailored thin plies, or the option of lowest cost. So that is using as thick material as you can, sort of few plies, very fast manufacturing. So three options there. You can choose whichever you need. You can go back and see the effect of using each. This data is not readily available, and it's come through essentially experience of projects I've been working on, and really what you can expect to buy these things for, these materials for. So yeah, it's kind of hidden, so it's not compromising material suppliers, but it's kind of got realistic costs of what you can buy materials in 2024 per kilogram at. So when you're done with the selection procedure, click Save, click Summary, and it'll publish all the decisions you've made. You can choose to edit those as much as you like. Then click Results, and it'll print out, it will show you a list of the selected options. That may be as little as 1, potentially up to 40. And for each of those, you can choose to list it in terms of weight, low to high, high to low, or manufacturing cost, and then start to interrogate benefits and issues. So yeah, that's how it works. It's worth, I think, pointing out who's been helping with this. The Composites Industry Cluster, funded through Bayes. AMSCI, funding LX. The Advanced Propulsion Centre at Warwick, and all the ARCS project partners, recently completed project. And here are a few of the companies whose information and advice have been built in. And yeah, so best wishes using the tool. Please give me a shout if you need some advice, and I hope you find it useful. Thanks very much.